seventh experiment. The title of that seventh experiment is stress distribution in a thick cylinder subjected to internal pressure only. It is internal pressure, it's not internal pressures, it is only internal pressure. Only one pressure is there. So title is stress distribution in a thick cylinder subjected to internal pressure. The aim of this experiment is, the title it suggests is that we need to determine what is the stress distribution in the thick cylinder when it is subjected to internal pressure. So that is the aim, to determine the distribution of radial, hoop and longitudinal stresses in a thick cylinder of given dimensions using the ANSYS software. So that is the aim. So coming to the problem description here, it is straightforward. A steel cylinder is 160 mm internal diameter, ID for internal diameter, and 320 mm outer diameter. If it is subjected to an internal pressure of 150 MPa, determine the radial and tangential stress distributions and show the results on a plot. Young's modulus of the material is 200 GPa and Poisson's ratio is 0.3. Since it is mentioned it as a steel, we will take Young's modulus as 200 GPa and Poisson's ratio is 0.3. He has given internal diameter as well as external diameter also given, and the internal pressure is 150 MPa. So asked us find out what is the distribution of radial and tangential. Your tangential stress is nothing but again it's a hoop stress only. Hello? Class lo unnaru nenu intlo unna class lo unna. So radial and tangential stress. Tangential stress means it is hoop stress only. So we need to plot something like this. If you see this diagram here, clearly I have shown the distribution also. So here this is the distribution of radial stress and this is the distribution of tangential stress or hoop stress. Of course, for a open-ended cylinder, that means we will assume here the cylinder ends are not closed. It is a open-ended cylinder. So for that, if you want to compute the longitudinal stress will arise because of the Poisson's ratio only. So that means, so if you use the equations of three-dimensional elasticity, your sigma longitudinal stress is nothing but mu times sigma hoop stress plus sigma radial stress. So that is only because of Poisson's effect you will have a longitudinal stress. If the cylinder is closed, so then in that case the longitudinal stress is nothing but load multiplied by the load divided by the area. So that is a different issue. But here, since we are assuming it as an open cylinder, so the stress is in the longitudinal direction is function of this hoop stress as well as radial stress. Okay, so now if you look at this plot here, so this is the variation for the radial stress. So you can see that the radial stress magnitude is 0 at the outer radius, maybe outer diameter or outer radius, whatever you can call it as. At outer radius it is 0 and it is increasing parabolically. You can see the curve here, it is a parabolic curve here. So it is increasing parabolically, and at the inner radius it is going to be maximum and should be equal to Pi, means the given internal pressure. Pi is nothing but the internal pressure. So the magnitude of the radial stress at the inner radius, it should be equal to your applied pressure. And also you can see that it is a negative quantity. You can see here from the diagram, it represented this one as a negative. So negative sign is given here, positive sign is given for the hoop stress. That means always your radial stress is negative stress. Maybe at the outer radius it is 0. So beyond that, everywhere it is going to be only negative. So this is going to be the variation of the radial stress. Similarly, coming to the hoop stress, again the hoop stress is maximum at the inner radius and it is a minimum. It's not a negative or 0 at the outer radius. Still it is tensile only. You can see it is positive curve only. Even its magnitude is positive at this location. So it is a positive stress only, but it is minimum at the outer radius and maximum at the inner radius. If you want to compute that magnitude of this hoop stress as well as a radial stress, here you have a formula he has given. So at the inner radius, the expression for hoop stress is given by Pi into a square plus b square divided by a square minus b square. So that is nothing but here, where a in the diagram is shown that a is nothing but the outer radius, not outer diameter. Remember, in the problem he has given the diameter values, but here in these formulas we need to use radius. Even while creating the FE model also we need to use radius values. So our radii, not the diameters. Even though he has given in diameters, we need to use only the radii dimensions only while creating the FE model also. So A is the outer radii and B is the inner radii. So this is the formula for hoop stress at the outer radii. So inner radii. So then this is the formula for hoop stress at the outer radius. So if we substitute this, so he has given phi to us and A and B also given. So A is 320 divided by 2, that is 160 mm, and B is 160 divided by 2, that is 80 mm. So A is known, B is known, and PI is known. You can easily compute this one. So these are the analytical formulas, what I can say, theoretical formulas or analytical formula. Similarly, if you want to compute the radial stress here, in the numerator, whatever you have here, so you have to change this plus value to minus value, that's it. So you'll get the expression for the radial stress as well as hoop stress. So suppose if I want to get at the outer radius here, I need to replace this b square by a square. So a square minus a square by a square minus a square. So it will get only 0. Similarly, at the inner radius here, I need to substitute. So in place of a square, I need to substitute. So you have a formula here. So you can use that formula so that you will get the value here also. So anyway, so that is the analytical formulas for, I think you already know this, you might have studied this one in our earlier courses. So analysis of thick cylinders. So from that also you can pick the formulas for what is the variation for hoop stress and what is the variation for the radial stress also. Okay, so this is about the analytical description of this problem. Now how we can model this one in our FE software, that is ANSYS. So here you can model this problem in two ways. One way is either I can use, okay, so the analysis of this thick cylinder is based on our Lamèche theory. So if I want to use that Lamèche theory, I need to model this one as a plane strain problem. Or else, so I have another kind of option also there in this. I can model the same problem as a axisymmetric problem also. So generally, in case of any structural problem or whatever may be, whether it need not be structural problem, it may be heat transfer problem or any other problem. In order to model the problem as a axisymmetric problem in FEM or in the finite element method, so the problem has to be satisfy three conditions. What are those three conditions are? If the geometry is symmetric about the axis, that is the first condition it has to satisfy. That means the geometry should be symmetrical about its axis. Then the loading conditions also should be symmetric about the axis. That is the second condition. Then the third condition is the material properties also should be symmetric about the axis. So that means if I take this cylinder, so this length direction or longitudinal axis, we'll call it as longitudinal axis is the axis for the cylinder. So now, like what I said, these three conditions, that is material properties, load and geometry. Here load includes the boundary conditions or constraints also. Loads means applied pressures or applied forces and as well as the constraints in the cylinder. So if they are symmetric about this longitudinal axis, then I can model the problem as an axisymmetric problem. So here in this particular problem, so we have all those three conditions are satisfied. That means if I take a cylinder, we know the cylinder is nothing but if I take some rectangular section, if I revolve that one by 360 degrees, I'll get a cylinder. So that means it is geometry wise, it is axisymmetric. Then if you see that pressure, here he is applying the pressure, internal pressure is there. So now it is in this view, so this point is going to be your axis. So now it is symmetric about this axis also. That means if I if I take some sector here, if I rotate that one by 360 degrees, it is going to the same. So that means I can take any value for theta. So therefore, your load is also symmetric. Coming to the third one, that is the material properties. So since we are taking the steel as a material for the cylinder, so we know steel is a isotropic material. So isotropic material means, by definition, isotropic material means the material properties are independent of direction. So that means in every direction the property is going to be same. So that means now all the three conditions are satisfied now. So they are symmetric. That means if I talk about vertical axis, if I choose anything, any point or any sector, so if I revolve that one by in other direction, revolve by some other angle, then the properties are going to be same. So that means, so here this problem will satisfy the axisymmetric condition also. So that means I can model this problem in two ways. If I want to use a Lamèche theory only, so if you want to model the problem based on Lamèche theory, that is the plane strain model. So in case of Lamèche theory, the basic assumption is only that. So we'll assume that the strain in the longitudinal direction is constant or zero. So that is your Lamèche theory, main assumption in the Lamèche theory. If I use that one, I need to model this problem as a plane strain problem. So instead of that, what we are doing here is we model this. We'll make use of the second option, that is axisymmetric option, because here the loading material and loading material as well as the geometry. So all the three are symmetric about its axis. So I'll go for the axisymmetric model. So now to model that axisymmetric, so our FE model will consist of only the revolving section of the cylinder. So that means if I have a cylinder which is having both the inner and outer dimensions, something like this. What happens? Okay, I'll take a different brush. Okay, it's working. Maybe the color is here, it is coming out as something like black. No, it's not working. Okay. Okay, anyway, so I'll use some other platform. Okay. Take here black color, then okay, now it is working. Right, so this is I'll see whether it's a cylinder option. Okay, it is not available. Something like this. Okay, so this will be the section view. So if I cut the cylinder exactly at the center, it is going to look like this. Now in this, I want to model only a axisymmetric portion. That means, see here, if this is the length of the cylinder here, So now if I take this cylinder, this what I can say, this rectangle, and if I revolve this rectangle by 360 degrees, I'll get a cylindrical surface. Maybe okay, later I'll show that in the software. I'll show it there. Okay, right. So here our intention is what I want to show here is here. If I take my y-axis is something like this. This is y-axis. That is our axis of revolution. So for that axis of revolution, if I take this is the rectangle revolving section here. So that means about this axis, if I revolve this rectangle by 360, I'll get a cylinder with the inner radius is equal to this dimension and the outer radius is from this point to this point. This is going to be the outer radius, and this whatever height I am taking here, that is going to be the height of the cylinder or length of the cylinder I can call. So that means our revolving section is going to be the rectangle. So I need to define first what is the axis of revolution for this problem. Then I need to define the revolving section. So while defining this revolving section, what I require is I need to first define what is inner radius. That means from the axis to the inner surface of this rectangle or inner line of this rectangle. So this distance is nothing but the inner radius. So from the outer radius is nothing but this is the outer edge of this rectangle. So from the outer edge to the axis of revolution, this is going to be our outer radius. So now that's it. So once I done that, if I revolve this one, so for height, if you look at the problem data, I has not given anything about the height of the cylinder. So generally we don't bother about the height of the cylinder in case of this thick cylinder, because like already mentioned, it is the thickness, thick cylinder theory is based on Lamy's equation or Lamy's theory. So there the longitudinal strain is infinite. That means longitudinal strain is either constant or zero. That means it is based on the length of the cylinder is very large when compared to the other two dimensions. So that's why he has not given the length direction. So therefore, a length is immaterial for us here. So therefore, we'll choose as for our convenience. We can choose any value for the length dimension. That is not a big deal here. So that's it. So I can model this one now. So just first I need to create this rectangle based on inner radius and outer radius, and then I'll take some height value. So so that I can model that is going to be the section I have taken from the entire cylinder to revolve it. So I can solve the problem. Okay, for that now here, if I come back to again that one. So now you can see here what type of element we are using for this analysis. We'll use the same element what we are using in case of the previous problem, that is PN183. So which is a 8-node element. So having 2 degrees of freedom in X and Y directions, or 2 translations in X and Y direction. So only thing here is, so earlier we used it for the plane stress problem. Now we are using that one. Same thing you can use for plane strain problem also, and also we are using it as an axisymmetric element behavior. So that means after selecting the element, what you have to do is you need to select the axisymmetric behavior for the element. So that is the only thing you need to do. So I think I already showed you the FE model here. Like previous problem here also, I don't want to restrict only, I need to consider only this many number of elements and this many number of nodes. Because so whatever model I shown it here, it consists of 192 elements. So if you want, you can change that, because what is the approach we are following here is we'll use indirect approach to create this FE model. That means first we'll create only the revolving section. Then what we do is, as per our requirement, we can divide this one into any number of elements. So here our radial direction, in the length in the radial direction, see this is the inner radius and this is the outer radius. So that means the thickness of the cylinder, outer radius minus inner radius, is nothing but the thickness of the cylinder. Actually we need to find out what is the distribution of the stress in the cylinder, means across the thickness, how the radial stress is varying, how the hoop stress is varying. With that we need to calculate. So that means here the thickness is 80 mm. So outer radius is 160 and inner radius is 80. So therefore outer radius minus inner radius is nothing but the thickness of the cylinder. So that comes out as 80. So now here how many divisions I did that one? I divided the thickness into 16 elements. So 16 in the sense, so for every 5 mm thickness, I consider one element. That means I'll get the variation of stress across the thickness for every 5 mm. Suppose if I want to find the variation of the stress for every 2 mm, then what I need to do is I need to divide this thickness into those many number of elements such that I'll get for every 2 mm distance I need to get one node. So in that case, what you need to do for 2 mm, if you want to get, you need to divide this one into 40 elements, 80 divided by 2. So that means you need to consider your edge length as 2 mm. Here for 16 mm, I consider the 5 elements. If I want to consider 2 mm is the thickness variation for every 2 mm thickness, if I want to calculate the variation of the stress, I need to take the edge length as 2 mm. So like that. So depending upon our requirement, so we can choose the number of divisions or number of elements in the model. So if I change the number of elements, obviously the number of nodes are also going to change. So because your each element will consist of 8 nodes. So if I increase the elements, so now nodes will also increase. If I decrease the elements, nodes will also decrease. So that's why particularly I have not mentioned, only we need to consider these many number of elements and these many number of nodes. Of course, so if I take this 192 total number of elements as 192, whatever solution I got, that is close to the exact solution. So analytical solution, like I already shown you the formulas here. So here, these are the formulas. If you use these formulas, if you compute the variation, the maximum value for the hoop stress, it comes out as 250 MPa, and minimum value for the hoop stress, it comes out as 100 MPa. Similarly, for radial stress, the minimum value is 0. The maximum value is the applied pressure, that is 150 MPa only. Of course, it is negative. So actually, those are the analytical results. That is, maximum value for hoop stress is 250 MPa, minimum value is 100 MPa. For radial stress, 0, and it is minus 150. So if I take this 192 element model, so this is giving the somewhat close to the our exact solution. The error is going to be less than 1%. So I can go with this model also. Or else still, if you want to reduce the percentage of error, you can increase your number of elements. If you decrease, definitely your error will goes on increasing. If you take number of elements less than 192, definitely your solution accuracy will decrease. So that means the percentage of error will increase. So with 192 elements, so then it is giving a satisfactory solution. So that's why I given this one as a FE model for this. So now for the after that, so only thing is you have one result table, that is nothing but you need to find out from the software, you need to identify what is the value of maximum stress, minimum stress. Similarly, maximum radial stress and minimum radial stress, longitudinal stress, because it is not going to vary, it is constant because it is a cylinder. So like I already said, the strain in the longitudinal direction should be constant. So in order to have strain constant, stress should be constant. So that's why you are going to get this one as a constant value. Because it is an open-ended cylinder, obviously your strain in the longitudinal direction is 0. If you compute that, you will get 0 only with these stress values. If you compute longitudinal strain, so definitely it is going to be 0 only. Okay, so anyway, we are not looking at those stress values. Or further, if you want, you can take what is the one mesh stress value, or what is the maximum principal stress value, what is the minimum principal stress value. If you want, you can evaluate those things also. But while recording purpose, we'll note down only these values. Okay, so once you've done that, then the actual question is we need to plot how they are going to vary. So this is the graph which shows the variation of hoop stress, radial stress, and longitudinal stress. Now this color, blue color, will indicate that it is going to be the hoop stress, and maximum value with that FE model regarded as 249.643 MPa, and the minimum stress, if you see, it is close to 100 here. Similarly, this is the variation for the radial stress. So here it is 149.64 with that model we are getting, so which is close to 150. So here it is going to be 0. Then this red color line indicates it is a longitudinal stress. You can see horizontal line means it is a constant. In the graph, you got a horizontal line means it is a constant. Its value will come out as 30 only. So at any radius, it is going to be 30 only. Even though you have a variation for hoop and radial stresses, but your longitudinal stress is constant. So in order to maintain that longitudinal strain is equal to 0, right? So this is how you can plot it. So only thing what you need to do is you need to note down this. Then you need to take this. You need to plot this curve for the variation of the stresses. Okay. Now I'll take you to the software and I'll show you how you can solve this particular problem in the software. So I already opened the software. Okay, maybe not yet. Okay, it is already open. Okay, so I'll close this. Okay, so I given the title as stress distribution in a thick cylinder. If I save it, so whatever files created by saving this file, so those are written in the name of this stress distribution in a thick cylinder. So first we select the element type, which is plane 183. For that, I need to go for addition of the element. I need to select solid here, and I need to select plane 183. So it comes out here now. So similarly, in previous problem, in the options earlier we selected plane stress with thickness option. So now I need to select this one as axis symmetric. So the second option is there. So we need to define the element behavior as axis symmetric. Okay. Then we need to define the material properties. No real constants or no sections are required for this. I need to define only the material properties. So I'll go for structural, linear, elastic, and isotropic material. In that, Young's modulus is 200 GPa. Since I am taking everything in mm, I need to define it is 200 E3 MPa or 200 E3 Newton per mm square, and Poisson's ratio is 0.3 as given in the problem. So once I define the materials, then I'll go for the modeling. So first we need to create the revolving section. So in the software, the default axis of revolution is going to be y-axis. So whatever it may be the problem. So always in the software you can define only y-axis as your axis of revolution. So provided if you plot your revolving section in xy plane. Suppose if you plot your revolving section in a yz plane, then again your revolving section is y-axis only. So like that, or else if you plot your revolving section in zx plane, then that is going to be your z-axis is going to be the axis of revolution. For simplicity, what we'll do is we'll take only xy plane and y is our axis of revolution. So for that, first I want to create the revolving section. Like I mentioned, we need to create a revolving section is something like a rectangle like this. So for this distance from this axis of revolution is that is inner radius, and this distance is outer radius. So I'll use that option. So for that, okay, I'll go for a rectangle. Straight away, I'll create a rectangle. So to create a rectangle, I'll go create areas, then rectangle. I'll use bidimensions option. So now it is asking for x1 and x2 coordinates, y1 and y2 coordinates. If you look at this figure, x1 is nothing but the x distance of this line. So that is nothing but your inner radius. And x2 is nothing but the distance of this line from this y-axis, that is nothing but your outer radius. That means your x1 corresponding to the inner radius and x2 corresponding to the outer radius. Then y1 means, so from the horizontal axis, this horizontal line, bottom horizontal line is at what distance and top horizontal line at what distance. This is the distance of the bottom line is y1 and distance of bottom line, top line is going to be y2 from your x-axis. So what I'll do is, for simplicity, I'll take this one as 0 itself. So that means this bottom line will coincide with the x-axis. And the top line means, suppose whatever length I want to consider, I'll take that one as the y-axis, y coordinate for the top line. So let us take as some 60 mm is going to be, or whatever may be, whatever value you want, you can take it. It is not an issue, because only thing is, we are not modeling the entire cylinder. We are taking only the portion of the cylinder. So whatever height you want, you can use that height. So here I'll use 60. So this is 60 is only one number only. So if you want, you can use any number. It's not an issue at all. So now first x1 is nothing but your inner radius, which is 80, and x2 is outer radius, which is 160. Then y1 is the bottom line y coordinate, which is 0. Then I am taking the height as some 60. Then okay, click OK. So now if I go for fit view, so this is the rectangle what you are going to create for that model. So this is our geometric model. So once you create your geometric model, then next thing what you need to do is you need to convert the geometry into FE model. So for that we need to use mesh tool. Go for mesh tool. Then before going to mesh, like I mentioned, how depending upon the edge length I am choosing. That means depending upon my requirement, how many number of elements I need to make in this FE model. So that you have to specify. So that I can specify here through the edge length. So under size control, if I click on global set here, so now I am defining the edge length here. So in order to get that 192 elements, I need to give the edge length as 5. Or if you want to go for more number of elements, you reduce the edge length. So like I mentioned, if you want to have a stress variation for every 2 mm 2 mm thickness, so you need to go for edge length as 2 mm. Now here I am taking for every 5 mm edge length, I am taking the stress value. So therefore I am giving it is 5 here. Like that, whatever you want, you can do that. So then only I not mesh that. So simply I define the edge length only. Then to mesh it, I need to go for mesh here, click on the mesh, then select this area, then click OK. So now it is converted into FE model now. So now if I want to see the number of elements, I'll go for numbering. Here I'll select element numbers on, then click OK. So now you can see that maybe, okay, so you can see here, this is 190, 191, 192. This logo is coming underneath that. So it is, there are 192 elements. So, or else you can, if you want, you can list also. Go for list number of elements. So you can see here also, you can see the total number of elements is going to be 192. Or else, if you want to see the same view what I have shown in that document, for that, what you have to do is, you need to switch off the colors. So I want only numbers, so that I'll get only black and white. So now you can see clearly the number of nodes also here. So in each line there are 16 elements. So in the vertical direction you have how many number of divisions are there, because 60 by 5. So 12 divisions are there. So you will get 192 elements like this. Okay, I want to keep that again on. Colors is required while plotting the stress values. Okay, so this is about the finite element model. So what I'll do is plot multiplots. I'll switch off the numbers. Okay, what I'll do is I'll go here. I'll go for no numbering again. So that is only for our visualization purpose only, to understand how many number of elements are there. Okay, so now we need to apply that internal pressure. And then after that, we need to apply some more constraints, because we are not taking the total length, we are taking only the portion of the cylinder. So we need to apply the symmetry boundary conditions. So for that, I'll go for define loads, then apply structural pressure on lines. So like I already mentioned, this line will represent the inner radius of the cylinder, and this line will represent the outer radius of the cylinder. The pressure is applied, internal pressure means pressure is applied at inner radius. So I need to select the online option, and I need to select the inner radius. That means this inner line. Click OK. Then here you need to enter what is the magnitude of that pressure. He has given that one as 150 MPa. So we'll enter 150 and click OK. Don't apply minus value, because pressure is always pressure only. So it will act towards the body. See, you can see that the arrow is pointing towards this inner radius. That means it is pressure only. So this is the load. Then what we need to do is we need to apply for this line and for this line a symmetry boundary condition, because actually our length of the cylinder is infinite, so are very long. We need to consider very long cylinder, but instead of modeling the entire length, what I did is I taken only a section of length, so that it is by assuming it is symmetric about this point as well as this point. So therefore we need to apply the symmetry boundary conditions for this. So or else you can go for displacement constraints also. Either way it is going to work for you. So better thing is we'll go for the symmetry boundary conditions. So in order to apply the symmetry boundary conditions, what you need to do is you click on displacement here. In that you have an option for symmetry boundary condition as well as anti-symmetric boundary conditions. But we want to apply the symmetry boundary conditions. I'll click the symmetry boundary condition. Then I'll select the line options. Then I'll select this line and this line. Okay. So that's it. So this is how we need to apply the loads and boundary conditions. Once you've done that, everything is okay. Our solution analysis type is only static analysis. No need to change anything here. If whatever default things is there, those will work for you in this problem. So no need to change anything here. Straight away again can go for solve and then current load step. So click OK. So it will solve for you. So if you do everything properly, it will solve. So list is done is comes out here. So then I'll save this now. So after solution is over, and now we need to look at into the values. So stress values, we require stress values. Either you can list the stress values or you can plot the stress values. So first I'll plot the stress values. So here we have to identify what is the radial stress direction, what is the hoop stress direction, and what is the longitudinal direction. So in this problem, so like I already told you, y-axis is going to be the your axis of revolution. That means y-axis is the longitudinal direction, and x in the x direction, this we have taken this one as the inner radius and this one is the outer radius. That means our x-axis is going to be the radial direction. Y is longitudinal direction. Obviously, our hoop stress direction is going to be the z-axis. So accordingly, I need to plot the results here. So contour, go for plot results, contour plot, nodal solution. In this, I can go for stress, x component of stress, which will give you the variation of your radial stress. See, you can see that radial stress is, this blue color indicates minus 149.643. This is the minimum, that is the, in terms of magnitude, that is the maximum value. Of course, even though it is negative, but at the outer radius, you can see it is close to 0.025602, something like this. So this is the expected variation. So the radial stress should be the maximum at the inner radius and minimum at the outer radius. So we got the same results, and also if you take these values are close to your analytical solution also. So that means I can accept this meshing, mesh FE model. Or else still, if you want, if you think that this is still it is going to be 149.643, which is not equal to 150, then increase your mesh size. So we'll get it is close to 150. Even like this also, here actually you need to get 0 value, but still we are getting some value, 0.025. If you assume it is equal to 0, then there is no issue. Or else still, if you want to increase your accuracy of the solution, you need to go for one more step. That means you need to refine your mesh. So this is about this radial stress. Then I'll go for hoop stress. Hoop stress is nothing but the z component of stress here. So this is going to be the variation for the hoop stress. See, now the red color indicates the 249.643. So this here, this is the inner radius and this is the outer radius. Like I already told, the analytical solution is 250. Here we got it as 249.643, which is okay. Because the error is less than 1%, I can accept this solution. If not, if I want to improve the accuracy, then like I already told, you need to increase your number of elements. That means you need to refine your mesh. At the outer radius, it is 99.97. So close to 100. So okay, it is acceptable. So this is our hoop stress. And then if I go for longitudinal stress, that is y component stress, it should be constant throughout. See, at any radius, so like I already shown you the graph, it is a horizontal line. Means if you take either inner radius at the outer radius or maybe some other radius here, it is going to be the same and its value is equal to 30 only. Its value, minimum value, maximum value, both are 30. That means it is constant. So this is how I can plot it. If you want, you can take this on a, you have to take the image of this one and you can plot, you can paste these images in your record, so that you will get the variation for all those things. Or else, if I want to see the 3D animation for this also, so like I already said, if I take a revolving section, if I revolve that one by 360 degrees, I'm going to get the cylinder. See, now I'll show you how you'll get the cylinder here. So I'll go for style here. Then I'll go for symmetric expansion. Then 2D axis symmetric expansion, I'll take it. So first I'll show you full expansion. So now you can see that you got a cylinder here. So whatever length I have taken, that much length only I got it is, you got an open end cylinder. So this is the how the stress is going to vary from the inner radius to outer radius. Of course, this is the longitudinal stress, which is constant. It is showing something like this. But if I go for the other hoop stress, let us say z component of stress here. So now at the inner radius, it is showing red color. So inner radius to outer radius, how it is varying. It is representing the values also here, 99.97 to 249.643. Similarly, you can plot the radial stress also, how it is going to vary. So at inner radius, the blue color indicates that is minus 149.643. At outer radius, it is red color, it is approximately equal to 0. So this is how I can do it. If you take since I have taken length only 60 mm, it is showing only 60 mm height here. See, you can see that revolving section also here is representing here. If I remove the colors, I can easily see this also. See now, if I revolve this one by 360 degrees, something like this, I got the cylinder. So that means, see, this is your axis of revolution. So I have to take only the revolving section, something like this. Okay, so this is how you can plot the results. Or else, if you want to list the result here, what you can do is, you go for list results, click on nodal solution, then click on stress. You select any one of these three, X component or Y component or Z component. So you'll get all the values here. So Sx is your radial stress, Sy is our longitudinal stress, and Xz is the OOP stress. So if you want to, if you are interested only in the maximum and minimum values, to come down completely bottom, at the bottom it is given. So the nodal minimum value stress, these are the minimum value stresses, and these are the maximum value stresses. You can see that here, radial stress is minus 149.64, and this is almost 0. OOP stress is 99.97 and 249.64, 30, like this. And also at what radius they are maximum, if you want to know that. So for that, you can go for the node numbering scheme, and you can verify that, or else from these contour plots also you can say that where it is maximum, where it is minimum also you can easily identify that. Okay, so this is how you need to take either those one, but you need to note down the result and you need to fill the table with these results. Then you need to take the images of variation, whether in the 3D model, something like this, or 2D model, whatever you want, you can take it. So after that, what we need to do is we need to plot the variation. So variation of the stress. So for that, what I'll do is I will remove this axisymmetric expansion. So I'll go for only this one. Now what I'll do is I'll plot the nodes first. I'll see the nodes. Okay, these are my nodes. Now across the thickness, so that means the radius is changing from inner radius to the outer radius. How the radial stress is changing, how the OOP stress is varying, or how the longitudinal stress varying. That I want to plot that. So for that here, to plot that, first what I have to do is I have to define a path across which I want to plot the result. So the path means only from it will start at the inner radius, it should end at the outer radius. So first I need to define a path. So for that, in the software there is an option called path operations. So where it is? Yes, it is here, it is there. Go to path operations. Then first, like I said, I need to define the path first. So I'll click on define path. Again, you have to, there are some different options are there. Either by nodes you can define, for work plane, by location, like that. You can use these options to define that. But here I'll choose by location because I know inner radius and I know the outer radius. So I want to plot the variation across the thickness. So I'll use this option, by location option. Then you need to give some name to this path. So what I'll do is I'll give some label. Whatever you want, you can give it. Stress path, something like this I'll give. Then click OK. Then it is asking for, see, in the earlier case, if you see how many number of points you need to define. Here, default option is 2 points I need to define. Path point number 1. So that means inner radius. I'll give number is 1. Then what is its XYZ location in global Cartesian coordinate system? That is, inner radius is 80. That is, X coordinate is 80. Obviously, the bottom line I'll select. Whatever line you select, if you see the contour plots, they are independent of this cylinder length. So only they are function of radius. So therefore, I can give any value here. I'll leave them as blank. Then click OK. Then it will ask me for the second point data also. So now I need to replace 1 by 2. Now the outer radius I need to input here, which is 160. Then click OK. So then after that, still it is asking. So then you can cancel this because I need to define only 2 points. Already done that. So once you define the path, then we need to map that path or map onto path. What are your required results? So I need to go for map onto path. Here I want to define the stress values. So first I want to take a radial stress. So here a label for that radial stress is I'll give radial stress STR. Or whatever may be the radial RAD STR. I'm giving the label something like that. Maybe there is some restriction here in the software. You cannot give your own in any manner. So there are some letter restrictions are there. So therefore, I'm defining the label something like this. Then click apply. Then I'll go for OOP stress. I'll give the label number for OOP stress is OOP STR. Okay, OOP stress is nothing but your Z direction. So you need to select SZ here, click apply. Then longitudinal stress label I need to give longitudinal. So long LON STR, I'll give something like this. Then you have to select SY is the stress value. Then click OK. So now I mapped all those three results on the across this path on the path. So then now I can plot it. So you need to go for plot path item on graph. So then whatever you define the labels there, those labels will come up here. Radial stress, OOP stress, and longitudinal stress. Whatever labels I define there, they'll come up here. I need to select all those three. If I want to plot all the three in a single graph, or if I want to plot separately, I need to select independently. So I want to plot all those things in a single graph. So I'll select all the three and I click OK. So now you can see that. See this blue color. This is the ever radial stress, and this color. This is the label for the OOP stress. This is the OOP stress, and this red color is for the ever longitudinal stress. So like this, I can plot this. Similarly, whatever I have given, I need to take the image of this, picture of this, and I need to paste this one into your record. Or else, if you don't want to do this one, what you can do is you take a piece of graph paper and then you need to note down all the values of stress values and then use manually you can draw the curve also. So for that, what you have to do is like that already shown in the list results. So you can see the variation. How we'll get the stress values here. If I click this here, across the nodes, you have all the values here. You need to note down all those values and manually you need to draw the graph. Either way, it is okay. Either use the software itself to plot the graph, or if you want to plot on your own graph, you can draw the graph paper. On the graph paper also, you can draw it. So choice is given to you. Either you can use the graph paper or you can use this one. And also one more thing here is, I think nobody is writing the observation. So that is important point. You need to submit the observation as well as record at the time of valuation. So far what I am observing is just you are attending the class and you are leaving like that. So if you don't prepare the observation, you need to prepare the observation at the time point for all the experiments. Be careful about that. It will take a lot of time for that. So better thing is prepare your observation as and when the lab is completed. So that is a better way of doing that. Otherwise, if you keep pending for everything, so up to last class now, then it is going to be tedious task. So for that, then what I'll do is from the next class onwards, if you upload your observation, then I'll give the attendance. Like that, I'll create a link. So if you upload your observation, then only attendance will be given to you. So I'll place something like that so that it will make our task somewhat easier. Instead of keeping all the experiment till the end of the semester, you would do regularly whenever your lab session is done. You upload your observation at the time point so that you will get the attendance. So that way you are going to benefit from that. So maybe not from this class, from the next class onwards, I'll do like that. So you need to upload your observation so that you need to get the attendance for the class. Okay, so I think I completed this one. So this is what I want to explain. So now it is done. If you have any doubts in this now, you can ask it now. If everything is okay, then respond to that attendance sheet. Then you can leave.
Sir. Sir, observation record A4 sheets lo rasnanga sir. Record A4 sheets lo rasti saripodda sir.
Watch break avutundamma naku raavla correctga. If you want, you can type in the chat box also.
Sir, records A4 sheet lo rasnanga sir. Observation atla sir print తీపియాలా?
Observation notebook ఉంటది కదమ్మా.
అంటే సెపరేట్ నోట్స్ లో రాయాలా సార్, లేకపోతే ప్రింట్ తీపిచ్చి రాస్తే సరిపోద్దా సార్?
నోట్స్ లో రాయాలి అబ్జర్వేషన్ ఏం రాయక్కర్లేదు కదా. నువ్వు రాయాల్సింది ఏంటి, ఎయిమ్ తర్వాత ఏంటి ఎఫ్ఈ మోడల్, ఆ ప్రాబ్లం డిస్క్రిప్షన్ ఎఫ్ఈ మోడల్, దాంట్లో ఏముందో అదే రాయటం అంతే. అంతా రిజల్ట్ రాయటం దాంట్లో ఫైనల్గా అంతే కదా.
ఓకే సార్.
ప్రొసీజర్ ఏం రాయక్కర్లేదు దాంట్లో నువ్వు.
ఓకే సార్.
Okay, anything else? If it is everything is okay, then I'll close the class. I think most of you leaving the class. Okay, no issue. So I think nothing is there from your side. So okay, if you don't have any doubt now, then you can leave the class. Don't stay in the class. You can leave it now. Why is some people are joining again? Pawan Kumar. So anyway, I am closing the class now.